All right, recording started now. So thanks, for inviting me as well. So today I want to talk a little bit about this nice intersection between machine learning and constraint optimization. And really, it's going to be a biased presentation because I'm going to inject a lot of things that we have done in my lab. But you're going to see the theme, which is going to be based on this survey, now a couple of years old survey that we've written with the teams of my lab members. And this survey here, which is actually meant to be expanded soon with Tias and his students, so just a teaser. But essentially what we were trying to do here is to categorize, together with other researchers actually, that have also run surveys in this area, but we were trying to categorize this intersection of machine learning and constraint optimization because it's such an emerging area, but it's evolving so rapidly. And so we were looking at basically two directions, how you can use machine learning for improving constraint optimization solving, so like speeds, like Tias was mentioning earlier, like implementing branching strategies. Maybe you're going to hear more about this from Elias. And so on, as well as the other area is how to really integrate in an end-to-end fashion optimization and learning. And so here, what do I mean by this? And this is really the art of using constraint optimization either as a layers embedded in neural networks so that you can enhance the capability of those models, the reasoning ability of those models, or using machine learning to learn solutions of an optimization problem, right, in the so-called learning to optimize. And so I'm going to focus more on this area here today. And more specifically, I'm going to look at basically two ways of seeing these intersections. That of using machine learning for optimization. So how do we construct those so-called proxy optimizers where we want to learn solutions of our optimization problems, as well as optimization for machine learning. So how do we build differentiable optimizers and then how we integrate them into learning components so that we can achieve machine learning models that do have some extra ability, right? They satisfy some properties in the space of hypothesis. So let's keep this as interactive as possible. If you have questions, just feel free to interrupt me and ask me a question. And so let's get started with some motivation. I didn't know how high level we were going to be in the introduction, so I have just a very, very few slides to defining the nomenclature and the concept that we're going to use here. What I mean when we talk about constraint optimization, it's really the classical terms. We have a minimizer that has an objective function f, and the decision variable, in this case called z, are subject to some generic constraints. And then the form of the objective and the constraints are characterizing the difficulty of this problem here. So we talk about convex problems whenever the function that we are optimizing is convex and the constraints form a convex set. And those problems are nice. They are giving us some interesting theoretical guarantees, the existence of uniqueness of solutions, and typically we can have solvers that are efficient to find such solutions. Within this realm, we find linear programs and quadratic programs. And then we have different beasts. So when a subset of the decision variables takes on discrete values or integer values, we talk about mixed integer programs. Those are much more difficult problems because the feasibility set now consists not only non-convex, but it consists in distinct points, so it's discontinuous. Right? So here you have a completely different set of techniques to tackle such type of problems. They are much harder. They're typically NP-hard. And then nonlinear programs, where either the objective or the constraints or both are nonlinear, non-convex functions or sets. And so, once again, we can solve convex programs. We like those. Non-convex problems, we can solve them with some variants of algorithms that are typically adopted for in-convex optimization, like interior points, augmented Lagrangian methods, and so on. For MLPs, we require other set of techniques like branching, and pricing, like he was mentioning earlier as well, for some certain problems. And then CP, as nicely introduced by Tias earlier, it's a fantastic tool that is used in so many applications that merges reasoning and search. And so, continuing with this introduction, and again, you covered this beautifully, but I had this slide here just because I didn't know how much would have been introduced in the previous talks. But what we're going to talk about today is mostly supervised learning. And so this is the generic context where you're giving a data set, which is labeled, and we build parametric models that takes in data, right, X, and split out something, Y. And then we want this something to get as close as possible to our labels. And we are using a loss function to render this something that we're splitting out as close as possible to our label. And we typically call this forward interaction, the forward pass, meaning that we're just processing the operations that are defined in each layer of the neural networks from inputs to outputs. And then we have our backward pass in which we're computing the informations encoded in the loss, in the gradients, and then update through those gradients the model parameters so that we can do the actual learning to improve. We use our empirical risk function, so we're minimizing here the expected value of the loss functions over the model possible parameters as a generic tool here. Okay, so given this introduction, we can actually start with the real talk today. So the first part of the talk, it's going to cover the use of machine learning for optimization. So how can we build those optimization proxies, as I call them? And this nice integration here, it's motivated by many problems that are arising in engineering, actually, and scientific domains. Why? Because often, we encounter optimization everywhere, but in those domains, optimization is so vastly present that we might not even realize it. So, for example, if you think at transportation systems, energy systems, flood mitigation systems, they are all systems that are run by the means of solving some optimization problems, often in real time. And they really are crucial for ensuring social and economic stability. And so those problems have also been highly stable and reliable during the years. But now we are seeing that many of those systems have been challenged by several factors. So for example, in energy systems, the increase of stochasticity, which is driven by the presence of more solars, more wind powers, and more customary loads, has brought some difficulties in understanding what is the load profile that we need to match, what are the resources that we need to match. Similarly, in transportation systems, there are new return policies that we have, especially in the US. This has challenged the supply chain management. And so this is essentially creating a lot of uncertainty in supply and demand. And those supply and demands needs to be answered quickly. So this uncertainty needs to be answered quickly. And so to reply to those challenges, what system operators of these systems are doing, it's not really solving those complex optimization problems exactly, but they are solving some relaxation or some approximations of those problems. And in turn, those approximations, they bring some deficit in cost, right? And those costs can be measured in terms of economical costs, but also in terms of societal benefits. And so, to give you an example, if you take the electrical power system, this is probably the largest machine built by humankind. In the US alone, there's about $400 billion worth of electricity that is produced and shipped through the production systems. And this is also a massive catalyzer for climate impact. In fact, there is about 40% of the total carbon emissions that it is produced by the electricity of generators that are powered by the combustions of fossil fuels. And so if you think about that, those systems are run through a series of optimization problems. So increasing the efficiency of such optimization problems, even slightly, will have massive benefits, right, in terms of economical cost and societal benefits. And the problems that we're solving here are really complex. And so this is to give you an example of the problem that I'm dealing with. In a power system, you care about, you basically have three main components. You have generators, which are those large plants that inject power into the grid. Then you have loads, like customers and cities and so on, which are withdrawing power from the grids. And then you have transmission lines, where basically allow you to transmit powers from generator to loads. And the way, you're essentially seeking a flow problem. You want to solve a flow problem, but this flow problem is regulated by nonlinear, non-convex constraints because we need to take account of the physics of this problem. And so this is what it is described in the AC optimal power flow. So you want to minimize some cost objective, which is how much does it cost to run this power system, so that we match the load, the demand, while also satisfying the physical and engineering constraints. So the engineering constraints here are that we cannot generate more than what can be supplied, and so on, right? So this is a very difficult problem. It's non-convex, non-linear, and what typical operators do is to run linear approximations of this problem, which are substantially faster, but they are bringing also substantial optimality losses. And so here the question is, when you're building such type of approximations, there is an art, right, to build such approximations, and those approximations are problem dependent, and they don't really look at instances. And so here we're asking a different question, which is, can we exploit a distribution of instance to build more clever approximations? And how do we do so, right? And here is the idea. So, well, we have a problem like the following here. So we have our classical optimizer. We just parameterize it by some data. So we render this parameterization over D, the data set, more explicit here, just so that we can take these data instances as input into the objective function f and in the problem constraints g and h. And what we want to do is build an agnostic system that constructs, so starting from a distribution of instances, O of D, that constitute our data set, our training data, right? We want to learn an approximation, O tilde in this slide here, of the original problem. So take our optimal power flow. We want to find essentially, by the means of training a machine learning model, we want to find solutions or a mapping from inputs to solutions directly, right? And we want those solutions to be as good as possible. So what we do is you take your problem instances. For example, in the power system settings, they would describe variable number and type of loads, or maybe different type of power line characteristics, right? Anything that can changes your problem setting. And you take also as input the label, aka the associated optimal solutions that we can found by running a solver over these instances. And then we train a machine learning model, so we minimize our typical empirical risk function, except that we also should care about constraints. And so if you would augment your classical empirical risk function here with those constraints, this really becomes a challenge, because in classical ML pipelines, we can't reliably inject or guarantee such type of constraints. And so here we're going to see how do we use such type of information so that the solutions, aka that we're splitting out, try to obey such type of problem restrictions, right? And so one idea that I want to, so is the setting clear to everybody? Can you raise your hand if it is not clear? Good. I was adding the note. Thank you. So, so to tackle this problem, one of the key techniques that my group has exploited is based on Lagrangian duality. So let's just review it very quickly. You take a minimizer, a classical minimizer. Here we're just considering inequalities. And you can build the associated Lagrangian dual function, which is just a weighted function of the objective and the constraints. Here, this is parameterized by lambda, the subscript of f. And this is actually the classical Lagrangian dual function. You can also consider what's so-called a violation-based Lagrangian dual function, where all the constraints here are restricted to be non-negative, right? And then what we would like to do is reframe this optimization problem here so that we can find the best z, so the argmin of z, with respect to this Lagrangian dual, right, parameterized by lambda. And then to find the best possible relaxation of the original problem, we maximize, so we find best lambda, the largest lambda, across all possible Lagrangian dual functions. So we're going to emulate this setting here in an ML setting. Okay, so we don't have an objective function here, we have a loss. And so let's build the loss of the function that I put in a couple of slides ago, right? So the empirical risk plus the constraints. So this is what we're doing here. So we have the loss over our predictor, f of theta, so the parametric neural network. And we're adding here a notion of constraint violations. Those new essentially are telling me whether we're making up violations or not, parameterized by the weight lambda. And then once again, to produce an approximation of this original problem here, we can parameterize our parametric model by a vector lambda, so our Lagrange multipliers, and we can simply minimize our empirical risk function. So this is essentially just a loss function plus some penalty term, right? And then you can use your classic stochastic gradient methods to minimize it. But then to find the best lambdas, you have this external procedure that finds the maximum value for across all the lambdas while minimizing our empirical risk. Okay, so this will find our strongest Lagrangian relaxation. So operationally, how do you implement this? It's pretty simple. So we emulate a Lagrangian dual step. So in the primal step, what you do at each iteration, you care about finding a good primal, right? So finding a good approximator for your problem. Right? So we need to output the solution of a problem that are approximated, and what we do, we just run through the data set, and we optimize, so we minimize our Lagrangian empirical risk function, right? So this is just the empirical risk function, which is also augmented with the constraint penalty violation, which is in line 5 over there. And then, once that step is completed for one epoch, you run an update step, which simply updates the Lagrangian multipliers associated to each constraints, and this is done emulating a Lagrangian dual update step, right? So here we're essentially saying, how much do you violate the constraints given the primal that I have approximated in iteration k, and then we're updating the Lagrangian weights based on that constraint violation, right? And we keep iterating. And this is essentially what you do. The difference with respect to classical optimization is that you don't have to restart. Every time you find a new primal, you don't restart from scratch. You just reuse the weights of the network, so you always have a hot start. So the procedure is fairly efficient. And you know, how does it work? When we tried this on optimal power flow problems, we got quite some good results. So on the table on the left here, I'm showing what is the distance of the load flow solution. So what that means? That means that once we output a solution, once we output essentially any output from our machine learning model, that output is not guaranteed to be a solution. It's not guaranteed to satisfy the constraints. But we can easily project it just by run any solver and project that particular instance over the feasible space. And whenever that instance is close enough to the feasible space, it's relatively easy to run such type of projection. So this is what we're measuring here. So those are actual feasible solutions that we're measuring, that we're finding there. And what we're measuring here is the distance with respect to the closest feasible solution, right? So the highlighted blue entry is the industry standard, is the linear approximation that it's used in industry. And the red model is what I showed you earlier. And so here you can see that we have over an order of magnitude improvements just in solution quality, right, with respect to constraint violations. On the table on the right, so the first subtable shows how the suboptimality of the solution that you found. And so here we're showing that you're at least one order of magnitude on average better than the current industry standard. And finally, you have runtime. So showing, since after you train, this is just inference time, pure inference time, then these things are really quick. So you can run inference time in order of milliseconds, meaning that you're over 4 order of magnitude faster than the current AC solvers. So this technique works pretty well in these classes of problems, and there are some caveats to consider, but this really started a research area that we continued for a few years. Yes.
So there's actually no guarantee that fewer violations are actually more accurate. So is this the accuracy after the corrections?
No, that's before the correction step. So you're meaning the distance to the ACP of so the optimality gap? Oh no, that's before. Um, no, actually, I want to say that is after the projection step. So before the projection step, you end up being more precise because you're relaxing. After the projection step, yeah, you don't have a guarantee. I mean, but you don't even have a guarantee on a solve. This is an NLP, right? It's a really bad, difficult problem. So, but yeah, for the moment, for these slides, there is not an end-to-end, integration of that projection step. Later there will be. So we were happy. This seems to work, but then we also want to know why, right? Why is this model here ending up approximating pretty well, pretty decently our hard optimization problem? And so the first thing that I wanted to notice is that, okay, let's do this with an illustration. So if you look at the plot on the top right over there, what we're showing is on the x-axis, we have an ordering over the problem instances. So what we're doing here, okay, think it's a classical flow problem where you have some demands that you want to match, okay? So what we're doing is we're modifying those demands slightly, right? So you modify the demands and you build new instances. Basically, you're simulating a collection of scenarios that are happening, across several days, but then you can enumerate them, right, based on these demands. So, and the 0.8 would mean that if you have a nominal test case, which would be at 1, 0.8 might be a little bit under, you receive a little bit less demand, 20% less demand, and then over 1, you receive more demand than usual, and so on. And so when you do that, and then you plot these solutions for the generators, then the generators are essentially outputting some power. So on the y-axis, you see the power that is outputted by the generators at a given, for a given demand vector. When you're doing that, you end up creating some kind of solution trajectory, which they really look like piecewise linear functions, right? And so this plot here is just to illustrate that when you train a network, an architecture that has ReLU function, which are those dotted line, they do a much better job in capturing those piecewise linear functions than one which is trained on tanh activation function, which is that, how do you call it, that other lines, the dashed lines. And this is, in Insight, it's intuitive, it should be intuitive. We know there is a result by Hang et al. In 2020 that actually proves that ReLU neural networks are exact approximators of piecewise linear functions. But then, in this example here, we also understand then that those networks here are thus compatible with the task of predicting solutions, but this also relates that ability of capturing the solution with the model capacity. So how large what is the capacity of our model that is sufficient in order to capture exactly such type of piecewise linear functions. And so we, in a recent result, we characterized this, the model capacity that is required for a ReLU neural network in order to capture exactly or within some tolerance such type of piecewise linear functions. And so this essentially tells you something. It tells you on how complex this network should be, but also it tells you that automatically, easier functions, easier piecewise linear functions should be easier to learn. And so what you see here on the bottom plot, you see kind of an illustration of how easy, quote unquote, are the outputs of generators that we want to learn. With respect to this notion of piecewise linear complexity. So the complexity here is just measuring the number of pieces and their total variation, right? The more jitter you have, the more difficult it's going to be to learn this hectic function, right? And so here for very simple outputs, you have a little error as outlined on the y-axis, and then the more this complexity increases and the higher those errors are, right? And here I want to say that there is no notion of constraints. This is just a plain ReLU network minimizing the classical, empirical loss function. Now, given this, and given this result here, so more capacity means that you should better able to capture those piecewise linear function, then we thought, okay, let's increase the model capacity so that we can reduce those errors. And let's see how much we can push those simple ReLU network without constraints. And so what happens here is that we increase the model capacity of about an order of magnitude, a bit more than that. For a variety of generators and for a variety of test cases and so on, we didn't see much improvement. And so this was interesting, and thus called for some further inspection. And so what happens here? So to understand why this behavior occurs, we examine, again, with this example, with this particular problem here, what happens for the solution trajectory of some generators that shows this more unstable piecewise linear trajectories, right? And so the shaded area over there, so on the top, first of all, you have the piecewise linear function that are induced by the solution trajectories for 3 generators. The dotted lines are their upper bounds, defined by their electrical constraints. And the shaded areas denotes the areas where you have these jumps, right? You have more instabilities. On the bottom plots, what I'm showing is completely unrelated variables. So those are voltage variables. They are, you might consider them as auxiliary variables. They are actually regulating the power flow, but they are not variables we're technically interested in here. But they are important because they are connected through those generators via constraints. And so what happens here is that when you see that shaded area, you see that voltages for several buses, they are touching their upper bounds, they are touching their constraints, right? And so what this is telling us is that the network that we try to learn that did not have any representation of the constraints essentially misses this type of notion here, because it has no idea that there is another variable that might touch an upper bound of a constraint, and thus it cannot penalize that type of behavior. When we introduce constraints through the Lagrangian-based methods or any other methods that you like, those behaviors largely disappear, and you're obtaining more precise solutions. And so this, I think, personally, this was a very interesting result for me, because when I thought about the first problem at the beginning, yes, I was excited about the results that we got, but then I kept thinking at it as simply as a regularizer, right? But then those results are actually telling us that, no, this is not regularizing that function. You're actually embedding more information, the information of the constraints, which is important per se. And it's something that is not captured by the loss alone. So there is that. Now, any questions? Cool. So those are, so far, I told you a little bit, hand-waving, how those problems can be learned, and more or less what should we do with the scalability and their size. But those problems that we want to learn, they can be massive, right? And so think about this. We have, for example, networks of, say, 1,000 buses, right? So the inputs of your network is a vector of maybe size 2,000, because those quantities are typically expressed as imaginary units, so you have 2 units. And then the outputs might be a vector of size, say, 2,000 or 4,000, right? So this is essentially a multi-level prediction that has an output space which is huge, right? And the representation that you need internally, it's also pretty large. So those architecture here, the network that we're using here can grow pretty large. And so how do we scale up those problems? Well, luckily, a lot of problems that we're dealing with, they also exhibit some structure. And again, we can take lessons learned from optimization and apply them into such type of context here. And so, for example, if you look at power networks like this one illustrated here in the slide, those networks are typically organized in voltage levels, and they are loosely connected. So there are components which are loosely connected across each other. So what we can do is to exploit our knowledge of optimization in order to improve the scalability of those problems. And so we can do that, in this case, by using a Lagrangian decomposition approach. So Lagrangian decomposition works as follows. You take a problem, right? Your minimizer with some constraints. And then what you do, you decouple the loosely connected parts right, of your problem by introducing some additional variables, right? In this slides indicated with x prime. And then what you're doing is simply adding an equality constraint so that those new variables that you have added, those x primes, will match with respect to the original variables, right? And then once you do that, this leads to two new subproblems that are loosely coupled, right? And you can solve them independently, and there is only basically a constraint that you need to match, that equality constraint. So we can emulate this process here. And this is essentially the deep neural network that you would end up having. You would train in this example, three neural networks independently, right? And then what you do is that after each training cycle, you would connect the variables that you've added through an equality constraint. And so you use that penalty function, right, the equality penalty function, in order to instruct your new loss of how far are those new variables that you have introduced, right? So it's an interesting kind of like finding from optimization and use that in the training of deep networks. How does that work? Well, with such type of tricks, now you can scale up to really networks of arbitrary size in the context of power system. So those are some of the results that which we obtain over the French power systems. So those are network with, I think, over 14,000 buses. So meaning we have over 28,000 variables and over 28,000 outputs. So you can scale up these things pretty nicely. The errors of each prediction variable here are low. The inference time, it's extremely reasonable, 2 milliseconds. So this is really nice. Okay, so now obviously all the considerations that we have done so far, need to. So if you ask me, does this work for every problem? Then I'm gonna tell you no. This is something that those type of proxies. So this building a mapping from a set of a distribution of instances to some output variables. It's something really interesting, really nice. But you have to have the right structure. You have to have the right problems. There are several classes of problems which also happen to be important in engineering systems, for which this works pretty well. But then when you try to adopt this in other contexts, you can take inspiration from such type of techniques, but further considerations are needed. So for example, we were really excited about those results, and thus we asked, why not looking at discrete problems? And now, those problems are completely different. Basically, here we ask the questions, can we really learn to represent the underlying combinatorial structure of problems, right, through these techniques? And we took a look at scheduling problems. Why? Because they're interesting. They're really, really complicated. So those are combinatorial optimization problems. You're giving a set of jobs of varying processing times, and that needs to be assigned to a set of machines with varying processing powers, and you want to minimize the total make span, right? So that is the length of the schedule. So those are combinatorial problems. They are incredibly hard to solve within real-time or short-time constraints, right? And we are interested in settings such as you're in a factory production planning scenario, stopping the factory if some damage arises. It's really expensive, and rescheduling everything, it's really expensive. So how can we respond to maybe a slowdown of a machine or a malfunctioning in quasi-real time? So the first thing that we did was, okay, let's take our Lagrangian formulation and let's apply it here, and let's see how does it work. And I can tell you, it doesn't work. It's really difficult to let it work. But let's see why. So firstly, I want you to look at this video here. So this video is representing an instance taken from the CPS lib, where we have tasks which are assigned to certain machines, and in the colors you see those tasks, right, and their durations. And what we're doing here is something similar to what we have done for the power system scenario. So we are taking some machines and we're slowing down that machine 1 second at a time. So we're simulating a malfunctioning to that machine so that it takes longer for that machine to finish the production of a task. And what you can see here is that even if you're just slowing down a machine by 1 second, you can see those task assignments jumping really rapidly. And this is why. Well, because when we're generating those solutions, we use CP Optimizer. You can't generate solutions in a optimal solution in a reasonable runtime. And also, this is a space which is rich of symmetries. So symmetries combined with whatever is the inner heuristics that is adopted by CP Optimizer renders those solutions to be highly quote-unquote unstable, using an ML term. But this is just an artifact of the presence of symmetries here. When you're presented with such type of data, if you try to plot those solution trajectory objects that I've introduced earlier, they look like the top plot over there. They're extremely hectic, right? So the number of pieces that this function would have, it's enormous. And so here we really thought, well, it's hard to learn those problems because really the data that we have, it's not amenable to learning. And so what can we do? Can we construct better data sets while being, in a sense, preserve the fidelity that we would have if we just use the standard methods? And so if you think of this as an optimization problem, this is really a bi-level program, which is outlined here. What you want to do is you want to find the best labels, so the best solutions, the optimal solution to your scheduling problem, while also at the same time minimizing your empirical risk function that approximates such solutions. So it's like, how do you build the best data set for this learning solver? And this is obviously intractable as a problem, but it gives us an idea, right, of what we want to do operationally. So we want to solve our classical empirical risk minimization, but across all optimal solutions. Yes? What is F without theta? So that is essentially the actual optimizer. So let's say this is CP Optimizer, this F without theta. So it's our, the objective of your optimizer, right? And so, right, what you want to do is, okay, let's find the best approximator, F of theta, such that my original optimizer, F, would do its job. It's find the optimal solution, right? So you, across all the optimal solutions, you have many, you have symmetries. Choose the one so that you build a distribution of data sets that allow me to learn well. So how do we do this? Well, we can't solve these problems. This is intractable. But given the theoretical results that I was mentioning earlier, and given that we had some additional results relating the difficulty of learning such type of problem with also a measure of their approximation. So we measure this difficulty of the piecewise linear functions through a Lipschitz component. So the larger essentially are the jumps that you have in this piecewise linear function, and the harder it is to approximate them. So given this intuition here, we can transform the previous problem into the following problem here. So we want to now find problem instances. Why? So those are the solutions of our scheduling. We want to find a distribution of problem instances such that when we're ordering them, right, the solution I plus 1 and solution I are, if they are close to each other, we also want their induced solution to be close, right? So we want to enforce some sort of Lipschitz condition across this, right? So if I slow down the machine just by 1 second, the solution induced just by slowing down this machine just by 1 second should be similar to that where the machine was not slowed down by 1 second, right? It shouldn't change too much the schedule. This is essentially what we're doing here. So we construct this method, it's pure optimization, and we construct a new data set. And now we play the video. Oh, I think there is a result. OK, so if you do this, the top subplot shows now the solution volatility, right? So this becomes much more stable. You see the induced piecewise linear function. It's much more amenable to learning. And the test loss here become much lower, so over an order of magnitude lower. The star indicates the projection of the solutions that we found from the network to the feasible space. So earlier, Basically, you find something, then you project it to the visible space, and it gives you a completely different thing. And while here, you can see that those projections are actually close to what the network finds. And so this is what happens. So this is before and after, right? So this is the data that you're producing normally just by running CPU Optimizer, and this is the data that you're producing by running this routine here. I promise you this video is playing. It's actually playing. And there is a jump, if you notice, at a certain point, but essentially those solutions are much more stable, right? And so it's natural to think that they are more learnable. But I think this point is interesting because it essentially tells us that there is also another axis sometimes that we might want to optimize, right? The data distribution, especially in contexts like this, where we have the freedom of finding solutions that have equal quality. And I need to mention that all the solutions that we found are found within a bound of the quality with respect to the optimal solution found by the CPU optimizer within a time limit. So this gives us greater flexibility. So how does this work in practice? So here are some results. We're showing on the y-axis the optimality gap, on the x-axis the runtime. So how long does it take you to get a particular optimality gap? The blue curves are CPU optimizer, and the red star here is the solution returned by the neural network. For the first subplot, you can see a negative optimality gap. That is because the CPU optimizer was run to produce instances with a timeout of 30 minutes. And so in this case, it just so happened that you find solutions that are better than the distribution of instances that were generated. But we actually verified by running CPU optimizer for 6 hours that that curve will go down. So matching and outperforming the red star. But what is important here is really to see that you can find solutions of extremely decent quality for a small fraction of the runtime, order of magnitude faster. And obviously, you might not want to run CPU Optimizer if you are in a context of real-time planning. You might want to run some heuristic. And so we tried with a series of state-of-the-art heuristics, and the neural network methods, we show that it's substantially better on all those heuristics, both in terms of runtime and in terms of solution qualities. Okay, so all what I told you so far was essentially the art that goes into modify our lesson learned from optimization and put them into a learning context. But as in optimization, where we usually wear a modeling hat and then a solving hat, I think we also need to make that analogy here. So I talked about the solving hat in a sense, but if I put my modeling hat on, then you would notice that the architecture design that we have for to render those network actually usable, it's also quite interesting. So in particular, this is what happened for the architecture that we use for the optimal, so for the energy systems. This is essentially a multi-hat network where we're predicting different physical quantities, and then they are connected through some hidden layers via constraints. This one here is the network architecture that we're using for the shop scheduling, where we're dividing jobs layers and machine layers, and then using some hidden layers. So we have a set of ablation studies show that the choice of those architecture here actually really pays off when you're comparing to just learning an end-to-end, ReLU network. So that's also pretty interesting, conclusion. And we have no idea on how to create those those architecture, automatically. So it's a little bit of an art at this point. Okay, so just to summarize this part of the talk, we were motivated by the need of creating well-performing optimizers, which are approximating the solutions of actual optimizers, but also we needed to enforce physical and operational constraints for those optimizers. And so here the insight was to combine or applying optimization principle within modern deep learning networks. And so we have seen a few of them. We haven't applied this only in power systems or task scheduling, but also in transportation computing, enforcing fairness properties in machine learning, enforcing robustness in model pruning, and so on. So this technique, it's pretty versatile. So before I move now to the next part of the talk, which is going to be on integrating really machine learning with optimization through differentiable layers. Let me pause for a minute, and let me ask if there's a question or two. Yes?
Can this be used for like any Lagrangian decision?
If the question is, can it be used for?
Any Lagrangian decomposition?
Oh, any Lagrangian decomposition.
Well, any or just some
So the question is, can you use this for any Lagrangian decomposition? So there's, we tried this with a few type of decompositions. Lagrangian decomposition is one, so as long as you have the appropriate structure, that should do the trick. There's another paper of a collaborator of mine that has done Bender's decomposition. So this is also something else that you can do. It's a slightly different technique, but it's another level of decomposition that exploits those optimization proxy as subroutines, and then there is this mechanic, right, of building the Bender cuts on top of it. But yeah, that's a good question. You can be creative with the type of decompositions based on the problem at hand. Other questions? Shy audience. Come on, guys, it's afternoon. It's morning for me. Yes?
Can you put like this to the architecture the last slide?
Yes, that's easy. It was just here.
Can you comment on whether these architectures are invariant to the number of decisions?
Oh, okay. To the number of decision. What do you mean?
Just the size of the problem.
Oh, okay. Yeah, so the question is whether the change in architectures would result in invariant sizes of the output space. In this case, yes, they are invariants just because we fixed the output layer, right, to constraining it to the size that we need to have in the outputs. But we have no control, or we try with variable sizes of hidden layers, right? So the hidden information, the shared information between, for example, those machine layers and job layers can be changed arbitrarily.
Sure, but it expects
Yes,
a predefined number of jobs and machines.
that's correct.
And is there a reason why, for example, there are set-based architectures that you don't need to do that?
Yeah. Yeah, so that's a good point. So we haven't explored that, that aspect at all. So for example, we're currently looking at graph neural networks for creating such type of invariants in the inputs. But those are invariants in the outputs. But having a different, a completely different input space challenges such type of problems, because now you're creating multi-distributions in the inputs, and those you also need to make sure that those distributions, right, of samples, they all obey to some rules that generally allow you to have good training, right?
Sure, but
yeah, but in principle, you could do that.
because if you change one job, if one machine is down.
Oh, I see. No, yeah, this is invariant with respect to that setting. So yeah, any machine can be down, and it is invariant with respect to that setting. But the size of the inputs is fixed. But for example, if you're training on an instance, LA39, and you want to test it on an LA14, then that is not any longer possible. And the intuition over there is that you really care about one floor plan. You're managing that floor plan or that facility. And yeah, you typically don't add or remove machines that easily. If you do, you can retrain the network. Yes, the number of jobs. Exactly, yes. Yes. All right, good. So let's move now to the next part of the talk. So here, we're going to revisit a little bit the ML pipeline. So far we had data. We push this data into the network. We get predictions, and we want these predictions to give us some meaningful outputs. And so far, what we have done is essentially using the standard transformations, right, from data to predictions. That they're simple nonlinear transform. But nobody tells us that we have to be limited by such type of simple transformation. In fact, each layer can be as complicated as we want. So in the most general case, a layer can be an optimization problem itself, right? And so you can imagine then to have layers which are optimizations themselves, and thus the inputs to an optimization layer might be output of a previously solved optimization problems and so on. So why you might want to do this? Well, this is really interesting properties whenever you want embeddings to satisfy solutions of arbitrary structure. And it's really useful when you want to integrate domain knowledge, or you want to integrate hard constraints or physical principles directly within the embedding of an neural network, right? So how do we do this? Well, in the forward step, we don't have to change much. We can just run things as they are. In the backward pass, though, what we need to do is to update through our chain rule the information of the gradients given the loss function, right? And so here, what we do is we may have a loss function which is differentiable, but then we find a solution to a really complex mapping, right? So we found a solution to this non-smooth mapping, and then we would need to compute this Jacobian matrix or partial derivative, which is complicating our computational graph. Well, the computational graph really it's broken at that point, so by the means of computing this Jacobian here, we would reconnect, right, this computational graph. But this is essentially the challenge, and is also the question of central interest to many people in this audience, I think. So how do you do that? So in order to differentiate through optimization programs, there's a few tricks that you can use, but in summary, all of them are exploring some form of optimality conditions of a problem. They also depend on the form of the program. So for convex quadratic programs, a beautiful paper by Amos and Coulter showed us that you can learn the QP layers by taking the gradients for some loss function with respect to the model parameters by exploring the KKT conditions, which are sufficient and necessary conditions for optimalities. And I'm not going through the details, but essentially you obtain them by firstly having the Lagrangian of the QP, generating the KKT conditions, and then taking the differentials of those conditions. And then with those equations, you can form the Jacobians of any incognita of the system with respect to the any data and parameters with respect to the model parameters or another quantities. And so this works. There is a package that you can use. I think there are integrations in other packages, and Amos has made also this package here relatively efficient and GPU enabled. So you can play around with with such type of QP layers. When you change the form of the program, so if you look at linear programs, and Elise is going to tell you much more about this. But here I'm just going to tell you that you can't exploit any longer those conditions as is, because now the optimal solution of an LP might not give you useful derivatives. And this is because the Hessian of this function f here, it's 0. And so the intuition here is that you have discrete solutions, so moving the model parameters just by a little bit can cause discrete jump to a different solution, right? So this is challenging. There's a few solutions that have been proposed in the literature to allow us overcome this challenge. For example, you can add a regularizer to smooth out this function here, and then you can use the techniques from the previous slides. Or you can create a distribution of samples, and then you can basically stochastically perturb this optimizer here. And once you have this distribution, you can get the derivative of this distribution here, and which are approximated, but they can give you really good results. But yeah, so there are ways of dealing with those seemingly difficult programs, and how do we use them? Here, so a biased. So there's several applications that have been proposed, and here is something that we have done recently, which is I am very excited about because it allows us to use such type of optimization, right, as integrated into layers to confer novel properties to machine learning systems, right? And so here I want to talk a little bit about ranking systems. What are they and what they're useful for? So ranking systems are a very pervasive part of society. So we're ranking literally everything. If you go on social media, your news feed is ranked through some algorithms. If you run a search, job search, candidates, and so on, they're all ranked through some criteria. And it is also important that this criteria that we're using to learning, it's some sort of non-transparent or hidden data that is adopting, and this is typically either user dwell times or click data and so on. So there is a lot of uncertainty in this type of data that we're using, and then we're using this uncertain data to build some ranking for such type of systems. Now, what you want to do in this problem of learning those rankings is essentially construct a mapping between a list of items that you want to rank and the permutation of this list, right? And there is a function that tells you how relevant are each items that you're ranking with respect to their position. Now, the idea here then is to form a ranking policy over which those permutations can be sampled, right? And what can happen here is the following. So there is also, while those algorithms are important, surprisingly, those ranking algorithms are agnostic to the implicit bias that they might have. So for example, if you run a query like CEO on an image search engine, then you could find that the results that you might have displayed disproportionately reflect males over females, right? Some mitigations have been developed recently on such type of problems here, but this is really the bulk of the question, right? So how can we reduce the disparate impacts that are arising across different individuals? So this is a property of the learning embedding, which we would like to have and to satisfy. So how do we do that? How do we learn that? And so here is the setting. So you have a query. A query describes something that you want to search, like the word CEO may be a query. And then you have a list of items. So the query defines some features. They might be the pixel of your image, whether it's a male, and so on. And then you're using a network to predict some relevant scores. And those relevant scores are then used to build this representation for our ranking. So this is the classical learning to rank problem, right? Now, in fairness, so in fair learning to rank, what we want to do is to also add a component that try to look at different groups and have those type of relevant scores there being displayed fairly across different groups. So something that you could do is use a penalty-based function, similarly to what I covered in the previous part of the talk. So what you would have is you have your empirical risk problem, and then you would say, okay, if I have, for example, males and females, I want that the average relevance of males to be equal to the average relevance of females. Or maybe their difference be bounded by some arbitrary constant. So you could do that, but as in the previous part of the talk where we had no control over the satisfaction of the constraints, so you don't have it here, right? So while you might impose those constraints, and those constraints might do something with respect to fairness, you don't really have the control of having a guarantee on fairness. And in fact, you can also have a false control on fairness, because you might guarantee fairness on average, but then for some queries, you might have arbitrarily large violations of fairness, right? And this happens for also in the constraint case. So how can we mitigate this? So here is an idea that you can exploit. So after you predict those relevant scores, the y-hat, what you could do is to build a program like this. So here, we're building, remember, we want to construct a policy over which we want to sample. And so what we're doing here, we're building a program, a linear program, which finds matrices, phi, and optimizes the discounted cumulative gain, which is a metric that we're using in learning to rank, okay? So those components that we're getting in the objective over there, the cost coefficients of the objective, are predicted by our neural network. They are YQ, right? And we're feeding them now to this linear program. And then this Y here will simply take a doubly stochastic form, right? So that we can simulate our distributions, our ranking distribution. And so this is just the constraints that we can add to our linear program. And then we can add some fairness constraint. In this case, we're just saying that the distance across groups, which evaluated with respect to our utility function here, needs to be bounded. We don't want males to be penalized over females or vice versa. So this is still an LP. Then you can solve it. So we can solve it through, so we can find solution, we can measure how good are those solutions through a notion of regret. And then for backpropagation, we're using some notions that will be introduced in a lot of details by Elias in a few days, which is the notion of SPO loss, which is essentially forming convex upper bounding over the original loss. And this works extremely well in practice. And what you end up having, it's an end-to-end differentiable pipeline, which runs into a linear program, right? And now, what you have here is then a system that, by default, satisfies, so the space of hypotheses that we learn in the system, by default, is constrained to satisfy fairness constraints, right? And so here are some results that we had over a few data sets. So the top plot display, what is it? Well, one data set, and the utility metric is on the y-axis. On the x-axis, we have some imposed fairness violations levels, right? We don't want fairness to be violated as more than x. The blue is our algorithm, and the pink and the yellow are penalty-based methods, state-of-the-art penalty-based methods. So the first thing that I want to notice is that you can notice that even if you are enforcing a certain constraint penalty level, those penalty-based methods, they are not necessarily enforcing that particular constraint, right? And in fact, with the colors here, we're denoting a particular fairness violation level, where darker color indicates smaller fairness and lighter color are indicating lighter fairness. So you should see a correspondence where the more you move on the right-hand side, the lighter those colors become, because you're satisfying less and less fairness. And so you can see this happening really nicely on our method, because that property is guaranteed. But on the other method, you see scattered colors here and there. So the promise is not satisfied, essentially. And the other interesting aspect is that this approach attains much better utilities than other approaches. And this is interesting also. And to explain why this is the case, so remember here you're making a prediction. So you're predicting those y, the relevant scores. And then you're using those relevant scores for a program, right? So you run them through a program. Now, when you're using a penalty-based methods, those relevant scores, they need to be quite correct, because you're using such relevant score to rank. But then when you're feeding those relevant scores as a cost coefficients of an LP, you can actually have a wiggle of an error, because the LP will find a feasible solution, and there is only a finite amount of feasible points whose objective values are different. And so here you can actually find a region under which these feasible solutions are regret optimal. And so you can find that even though you make a little bit of errors in your predictions, you can still find a high quality solution. And so this is a really interesting byproduct that we're having in this case. Okay, something else that you can do. So we looked at ensemble learning or model selection learning. So here what you do is you have a data set of samples, and then you have multiple models that are trained over these data sets. And what you want to do is to select a subset of those models to build a better predictor, right? This is a classical problem in machine learning, and you can use several type of voting scheme in order to select the best candidate selections. What we proposed here is that, well, if you see this problem here, you see the setting. If you're an optimizer, what you think about is the following. So I have a list of predictions, right? And I need to select a subset of them so that they're optimal with respect to some criteria. So, I mean, this is a subset selection, right? And so you can now frame this problem as a subset selection or a knapsack layer. And so what we did here is construct another network that predicts some coefficients, which is going to parameterize this linear layer, and this, I mean, LP layer. And here we have a subset selection problem, which is parameterized by this neural network. It splits out this unweighted knapsack solution here, so this 0, 1 vector, and then we can just multiply this 0, 1 vector by the output predictions of our models, and they will automatically select the best models for us, right? And then we need to train this selection here through a loss function, which is our classic loss function. And so we can do this. We use the trick from Bert et al. For backpropagation here. So we use the perturb optimizer. This works incredibly well, the perturb optimizer, in many settings. And we were able to obtain pretty good solutions. So here we're showing again in blue the constraint-aware solution. The y-axis is the quality that you're obtaining, the average solution accuracy, with respect to a number of heuristics as well as state-of-the-art models. And so here you can say that by varying the ensemble size, you find solutions that are typically much better than the solutions that you can find by normal, regular voting schemes or super learners. So this is another interesting setting where the combinations, really the integration of optimization and learning can provide some interesting, new reasoning ability, right, to the learning model, so that it is able to attain better results than the model itself. And okay, so yeah, I think I still have a little bit of time, but I don't want to focus too much on this because I want to leave a little bit space for questions. But if you have questions, again, please feel free to interrupt me. So far, the examples that I covered, they were looking at either convex quadratic functions or LPs. What if you want to go beyond that? So, or what other techniques you have out there that enable us to differentiate through those constraint optimization programs? As I was saying earlier, we need a way to exploit some optimality conditions of those programs. And so one way to do this, to solve this challenge here, is to use unrolling. So whenever you have any iterative optimizer, you can expand this iterative optimizer over your computational graph. And then as you go forward in the forward pass, you can simply go backward in your backward pass and have your Jacobians ready. So this is called unrolling. It doesn't work. So essentially, those iterative optimizer can have arbitrarily large amount of steps. And so you hit problems such as vanishing gradients or exploding gradients, you name it. And they are also extremely slow. But it's a way to also tackle such type of challenge here. And so we recently started asking whether you can do something better with such type of unrolling solutions. And we found some way to relate unrolling solutions with differentiable optimizers where you don't really have to go through all those steps of unrolling. And so let's take this step by step. Okay, so you have an optimizer, so you have a solver over there. And what we want to do is to define these solvers in terms of some iterative steps. So at each iteration k plus 1, you define the solution that you find from a solver by, this is given by a routine that we're calling u that takes as input the solution that we found at time xk, right? And then we continue, and this should converge in a finite amount of steps, right? Now, if the Jacobians of these functions here can be computed analytically, then we can avoid unrolling after all, right? Because we can just model the Jacobian path with the Jacobian vector product. So imagine now that I give you the Jacobian of this step here, u, analytically. So what you're left doing is not unrolling this function u, but just unrolling the steps x1, x2, x3, and so forth, right? So this intermediate step here, we call it unfolding. And it's just a step that's we're using in order to build some clarity on the fact that we are starting compressing this unrolled chain. And we're going to try to compress it all the way. So here in this, in this way, we're just unrolling, or we just need to make some computations on the outer iterations, right? All right. So there are two advantages of this technique here with respect to the classical unrolling. The first is that analytical differentiation of that function u allow you to remove all of those inner iterations, inner loops. And so this reduces the number of unrolled operations, and it gives you more stability in the training. But the second is that unfold optimizer can be converted analytically and can be differentiated end-to-end, and we're going to see it next. So following this idea, right, we have unfolded. We can keep unfolding, right? And if we unfold everything, essentially we go from start to end, meaning that we have a solver call, right? That solver call gives us the optimal solution. This was an iterative solver. It gives us the optimal solution. Good. Now we have that optimal solution. So, okay, just stand with me for a moment. So what you do, so this is illustrated here. So this we call it fixed point folding. So you basically call the black box solver. You give it the optimal solution. Now you need to compute the backward pass, right? Now, you have this solution here, and optimizing any iterative solution will generally require a starting point. And based on this starting point, convergence can be guaranteed to the optimal solution, right? And so the natural question, and here we're just showing, this is an unfolded PGD. We're just showing that the forward pass converges after a few iterations. Okay. And now the natural question that arises is also how does the initial state, the initial choice for x0, affects the convergence of the backward pass? And this is going to be important. So. And here we're showing, what happened with the backward pass. But essentially, you can show that when an unfolded optimizer is iterated at a pre-computed solution that was given by our solver call, okay, then the backward pass converges, but it converges at its own rate. So I want this to be clear, okay? What we're doing in this plot with the red balls here, we're just iterating at the optimal solution, at x star, okay? And the convergence rate here of the backward pass, it converges, but it converges lower than the forward pass. And why this is important? This is important because if in unrolling, you're not allowing yourself to have enough time to converge, say that you have an instance like this, where you have a forward pass, in blue in this case, which converges pretty quickly. You stop there. And then what we're keeping plotting here is the error, is the residual error of what you could have achieved in terms of precision of the gradients on the backward pass and what you actually had. So they diverge. So essentially, you're left out with the imprecise gradients, right? And so this can be actually arbitrarily bad, especially when you're using very specific step functions that are used to accelerate unfolding or other iterative methods. And so we characterized the convergence criteria in a recent paper of the backward pass. But the idea here is that even if you have an optimizer, you have a function called to an external solver, it gives you x star, you have this iterative solver, you need to keep iterating, right, in order to build exact gradients. So to build the information to compute that exact gradients, right? So the interesting aspect, though, is that because you're at x star already, producing the Jacobians, so the partial derivatives of our inner function u with respect to our point, does not have to be recomputed all of the time. You just compute it once, and you keep using the same solution all over and over, right? Because that solution has converged already. It doesn't change. And so the calculation is done only once. You just need to iterate until you get some convergence. And so we show that the convergence, the convergence is asymptotically proportional to the negative log of the spectral radius of the gradients of u with respect to x star. So so once again, this is essentially the one of the finding. But then what do we do with this finding here? Well, it so happened that with these iterative solvers, then you can build backpropagation rules which actually obey the same iterative natures that that you would obey in the forward pass. So as you have a solver call, a black box solver call to build your X-star solution, you can do the same by having a solver call that solves the systems of equations. There's more details in the paper, but essentially it's a linear system of equations, and compute exact gradients for your backward pass. Once you have that, you have a pipeline that does not require unrolling at all. Right? So we went from unrolling to unfolding to just a single point. Right? Everything is done off the computational graph, but it essentially obeys the principles of unrolling. And then we can start building procedures that go a little bit beyond what we can do with convex quadratic programs and so on. And so, for example, here we did some simulation on a bilevel program, a simple bilevel program, which was matrix Q are confounded by non-convex terms. And so this is just a simple decision-focused setting where we show that this unfolding mechanism, I think this was PGD, does its job, right? It trains better than the two-stage model. But also the other advantage is that now you basically can use external solvers. And so, for example, we looked at portfolio optimization, compared the speed of just iterating through SQP with Gurobi versus doing the same model with CVXPy, and then you can obtain much better results in terms of speed up. So the last results are over 80% faster than CVXPy. So this is pretty interesting because it frees ourselves to use basically any solver as long as we have those procedures in place. Cool. All right, so this concludes this part of the talk here. So we looked at the need of enforcing some structure directly in the space of hypotheses of learning models. So we integrated optimizer within the structure of a neural network, and we've seen this in several settings. All right, I'm gonna go through the open questions and then take some questions from the audience. I'm gonna glimpse over it. I'm gonna go quickly. But I think, so this is a super exciting area. I mean, I think each speaker here has a lot of enthusiasm because we're super excited about this area. I hope we're conveying such type of enthusiasm to you because you're the new generation of scholars that will need to make great discoveries in this area, hopefully. And so this is just my personal take on some of the questions that are still open at this point, or at least what makes me excited. So with respect to what I talked about in the first part of the talk, which is building those proxy optimizers. So those proxy optimizers are essentially, we're taking a network and they are specialization of a problem rather than generalization of a problem. We're taking a network and we're feeding that network into a specific data distribution. We're making that network really good in predicting some outputs that obey to that data distribution. How do we go beyond this step here? So how do we generalize to other problem instances, like Elias' question was suggesting earlier, or other settings, right? If I add a constraint and so on. How do we do this efficiently? And so can we, one of the questions that I have is whether we can transfer some knowledge from a dual space into the optimizer itself. There is also a lot of data need when we're generating data for such type of, for training such type of models, whether they are supervised or self-supervised, we still need to generate a lot of data. But sometimes we are not really generating this data effectively because there might be a lot of redundancy in terms of proximity of the inputs and proximity of the outputs in one region and maybe not in another region. Like think at what happened in regions where we are close to active constraints versus in region where we are not, right? So here, what can we do? Can we exploit other techniques like sketching, for example? So this is something that we're currently looking into. Some other area that I'm really interested in, it's also that of integrating such type of aspects with system dynamics. I'm really interested in the context of power systems, for example, where generators are not only regulated by actions of providing a certain amount of energy or not, but there is also some system dynamics that regulates the behavior of those generators. And those system dynamics are slow to compute. They are typically systems of PDEs or RDs, and those, we can't really recur to simulators if we want to solve such type of equations while also optimizing for operational constraints. And so here, what we started looking at is building approximations of those system dynamics with similar techniques of what I presented in the first part of the talk, and then use those approximated models within a proxy optimizer so that we can have a really fast interactions between simulators as well as optimizers. Now, there's a lot more open questions. I'm sure when our survey will be out, you will have the chance of reading many more. But a few of them are, so there's challenges that are now limiting the adoption of the techniques that I have reviewed in the second part of the talk. One is really the constraint that we have on the problem form. So in the last part of the talk, I presented one possible technique to overcome this challenge, but most of the technique that we have studied, they are limited in the problem form, either QP or LP or MILPS. So how do we go beyond that? The other problem is efficiency. So TS and his students have several works that try to tackle this problem here. So whenever we look at this integration of optimization and learning, and whenever we are passing through a layer that is an optimizer, at every training stage we need to have a function call to an optimizer. So how can we speed up such type of operations so that the training is actually bearable? And so how can we combine also such type of area? So what I presented in the previous part of the talk, right, and the second part. So for example, we're currently studying way of generating very precise or arbitrarily precise starting point for a solver, and then can we use the techniques that I presented here to build good optimizer that can project into the feasible region. And so this would give us an interesting way of constructing end-to-end solutions. In addition, I think we also need uniform benchmarks in this framework here, because we can't really grow if we don't have baselines. So it's something to ponder about. And so let me conclude just by saying that this integration here, the topics that you're studying of this summer school are extremely exciting. They are creating a promising direction. It's a very novel area with much work to do. And so I really hope to see a lot from you in the future days. I want to thank my group of students that have performed much of the research that you have seen here, and my sponsor, and thank you for the attention. I'll take questions if you have any. Yeah, should I stop recording here, or can you hit play? Yes.
Can you maybe go back to slide 60?
Yes.
Yeah, so here you mentioned that part of the reason that you get good performance, I guess, is you have multiple solutions that are different optimally.
Right. It's not really problem specific. It's just a property of the construction of this Birkhoff matrix. So essentially, you're constructing, this doubly stochastic matrix which has a certain form, and so you have to satisfy obviously that that type of structure. But generally, you have to think that the prediction that you're getting out of that neural network, classically they form a ranking per se, right? But when they are then used as input to this LP, then the outputs of this LP now has a new form, and that form imposes the restriction that those outputs should have had in the first place. So whenever you have, for example, problem instances over which you have disparate accuracies, right? This is going to arise. You may have a sub-distribution of instances in which you are very precise, others in which you are less precise. And this is really the key, the strength of the predict and optimize paradigm. It's something that I think Elias is going to go much deeper in his presentation. But yeah, that's a very good point. Yes. Say it again? Oh, yes. Right.
And here you're saying it's an advantage that there's multiple points that leads to optimal regret.
No, here, what I'm saying, well, in a sense, but essentially here what we're doing is this, right? So we're predicting some information, and all what I'm saying is that it's okay if you're making a little bit of error there, because that error is going to be fixed by running the LP, while in two-stage problems, that error might be exacerbated later on. So over there, the symmetry is instead where in the input-output solution. So it's like looking at Q and looking at X star over whatever I call it, pi star here, right? But instead, the errors here are in the prediction. And so it's in the previous slide, it's like making the errors in the intermediate hidden representation of the neural network. But yeah. Yes?
Have you done any reasoning on this in the sense that trying to achieve solutions that are not necessarily optimal, but close to optimal?
Mm-hmm.
Because optimal solutions might be hard to attain in some situations, so you're trying to aim for like a bigger solution pool.
In the LP?
Yes.
Yeah, I mean, so you can regulate the degree. Yes, in generally. So when you do, if you regulate the degree of optimality by relaxing the constraint, which is what we do here, then this is typically what you can observe. And there are those contrasting objective in a sense. The degree of optimality, which is upper-bounded by that dotted line over there. It's also controlled by how strict are your constraints, right? And so you can see that, yeah, you tend to be optimal when you enlarge the neighborhood over which those constraints can be satisfied. So yes, that's a good point. Yeah. Yeah, thanks. All right. Yeah.
Thank you very much, Nando.
Thanks.